right, good afternoon and welcome back to CS225. So a really quick couple of announcements here at the top of class. We have an MP due that is due tonight. So MP4 is due at 11:59 tonight. And exam 4, which we've announced for over a week now, and we have told you now for the third time exactly what kind of problems you're going to be able to expect on the exam. So when you open the exam, you're going to expect to see a problem that looks like MP4 in the sense that it uses STL stacks and STL queues. And you're going to find a problem that uses binary trees. Or trees that look like lab trees. So you're going to see binary trees as a second problem. So those are going to be two problems that you're going to expect to see. And there's a lot of different questions we can ask about those things. But the generic structure is going to be the use of trees and the use of STL stacks or queues. So those are going to be what you're going to expect to see. So you should definitely know those interfaces very, very well. There is one other thing. So there's lots of people coming in late today, in part because what's going on all around us? EOH. What does EOH stand for? Engineering Open House. So EOH is this amazing opportunity that lets usually upperclassmen, but we do have some sophomores and freshmen involved with projects, but usually upperclassmen show off the work they've been doing all throughout their school career and building some awesome projects and being able to show it off to the community around us as well as your peers, both professors and students. So I spent about an hour kind of walking around seeing different EOH projects earlier today. And I encourage you to do the same. It's a little cold to do the outside stuff, for sure. But it's a really fun to see everything that's happening. There's a solar car going on. There's various different kind of audio analysis stuff. There's amazing projects and sort of really cutting-edge work being done by students just like you right here on the Illinois campus. So this is an exciting opportunity to check out for projects that you might think you want to join as you become upperclassmen, or just ideas of things that people are doing and things that you can get passionate about and things you can get involved with. So if you haven't checked out EOH, I highly encourage you to go check it out. It's an awesome thing. So any other questions on announcement type stuff? Awesome. All right, so we're going to kind of review where we came from. So we've been working on an abstract data type. Remind me of the abstract data type that we've been implementing. Not a tree, not a binary search tree. The abstract data type that we're implementing with a binary search tree is the dictionary. So the abstract data type is a dictionary. Our implementation of that dictionary is being used, we're implementing it with a binary search tree. So we're using a binary search tree to implement a dictionary. And at the end of class, we left off with this, before we talk about where we left off, let's chat about this data structure to remind you about the abstract data type one last time. So we've got 3 key operations, which we've looked at 2 of them last Wednesday. So the first one we looked at was the find operation, which took a key and ideally returns a key and the data back to the user. So this was the first operation we looked at. The second operation we looked at was an insert operation that took a key and some data and inserted it into our dictionary. And the last operation we used, or the last operation we talked about that we have yet to implement is delete, or is remove. And the remove only needs a key, and it will not return anything. So the other operation listed here, traverse, is kind of a bonus operation. It's not included in a classical definition of a binary search tree or a dictionary, but you always kind of want the ability to go through all of your data. So it is very nice to have a view of all data. So one of the most frustrating things I have, the experience I have when I'm programming and using a library, is when the library takes in my data, and it may organize the data in a really intelligent way, but I just want to iterate through every piece of my data. So it can be extremely frustrating when you don't have access to a way to iterate all of your data inside some sort of a loop. So having that as part of a dictionary data type is pretty much considered essential, so that you have a way to actually look at all of the data in your dictionary. So as a reminder, all of our dictionary, or all of our binary search tree representation of our dictionary will be represented as this tree-like structure where we're going to list the key as all of these nodes, and then they're going to have an associated data component to it. So these might be a flower, this might be a tulip, or various types of flowers. Clearly, I'm not an art major. So this is our dictionary data type. Where we left last time was we had this implementation of an insert function. And the recursive case was basically pretty straightforward, but we did this nice, so there was code here, there's code here, there's code here. But the really key step was we did this line of code here in our base case, where when we found the node to insert, so if we were to insert 18, we said we need to go left, right, left to insert 18 right here. When we wanted to insert 18, we argued that all we need to do is say, this is going to be void, insert. All we need to do is say CRoot is equal to a new tree node key data. And we argue that this maintains the continuity of the tree. As written, I'm going to argue that this doesn't. What's different about today than 48 hours ago? Yeah. CRoot isn't being passed by reference. So if we think about the call that's going to visit the left subchild, so if key is less than this, our call, we're going to make an insert call to CRoot left. So when we make the insert call right now, we're passing it by value, because we're passing a pointer by value. So what's happening is, when we call insert, we're creating a value on the stack, and then setting that value on the stack equal to 18, right? So that's what's happening in the given code right now. What you'll see is that doesn't look like a binary search tree. Agreed? Because we're not updating the right pointer. At the very end of Wednesday's class, we said we didn't have to worry about this if we passed it by reference. So by adding an ampersand, so tree node star ampersand, so we still have a tree node pointer, but we're passing that tree node pointer by reference. What's happening now is, instead of creating a stack variable, the memory address is this pointer. So initially, this pointer pointed to null. And then when we drop into this first if statement, we say CRoot. We're going to update the value that's contained in that pointer. So now that value points to 18. because of where the memory location, or because the memory location that's storing the pointer changed, and we're passing it by reference instead of creating a new stack variable, we're able to maintain the continuity of the binary tree. So this is going to be something that you'll see over and over again as we spend almost the entire day today just talking about how to remove something from the binary tree. And you're going to see we're always going to exploit this idea that when we pass a pointer by reference, we can maintain the continuity of the structure. This is really awesome. It simplifies our code and makes it so that we don't have to think about our memory, and we can just worry about doing things very logically and write really syntactically elegant code. All right, and what did we say the running time of the insert operation was? It was not O of n. O of h, where h is the height. Yeah, so we say the running time of this algorithm is O of h, where h is the height of our binary search tree. All right, so, yeah. Okay. So let's talk about our final operation, the remove operation. And I'm going to even provide this code for us. So what we're going to do is we're going to sort of think about how we're going to write this code. And you'll see that any operation on a binary search tree is generally going to follow a pretty standard template. You've seen these last two lines before. Where have we seen these last two lines before? In insert and in, what's the other BST function we've seen? In find. So these two lines are the recursive case. The if statements are the same for find so specifically, these else if and else are the same as what we see in insert and find. So our recursive case is the same. We're going to make a call to remove instead of a call to insert. We're going to make a call to find. Whatever function we're recursing in, we're going to recurse that way through the same logic. Whenever we see whenever we're at a node and the key value is less, we go left. And the key value is greater, we go right. Pretty awesome. So now we say that the base case is we want to remove the node when we find the key. So for example, if we want to remove 37, we're going to go left, right, right, and remove 37. So how should we remove 37? What do we need to do? Yeah. Okay, so we need to do two things. So when we're deleting 37, we need to delete the memory associated with the tree node 37 and make sure that the pointer that pointing to 37 is now pointing to null. So that's pretty straightforward. So I'm going to say t.remove of 37 is pretty easy. So we just need to delete 37 and make sure that pointer points to null. So what are the class of elements that are that easy to delete? I heard a few of you guys say it. It's a four-letter word. So what nodes are easy to delete? Leaves. So all the leaves nodes in our tree are easy to delete. So these are all of the leaf nodes. So easy to delete, easy to delete, easy to delete, easy to delete, easy to delete. Okay. So what about deleting nodes that are a little bit harder? So is there a subcase that, are there some nodes that are probably easier to delete of the remaining nodes than other nodes? What do we think? Do we have a guess on what nodes those might be? So we've looked at nodes with how many children? 0. And now we can look at nodes with 1 child. So if we look at nodes with 1 child, let's say we want to delete 25. What does this substructure look like? It looks like a linked list. How do we delete from a linked list? Yeah, you set the kind of previous pointer to the next pointer, right? So we sort of skip. What we do is we now point 13 to 37, and we delete 25 and its associations. So now we have been able to delete the node by simply maintaining the continuity of the list. So deleting a node with 0 children, really easy. You can just delete it directly. Deleting a node with 1 child is very similar to what you guys found challenging 3 weeks ago, but now is really easy. So we're building up. So it's still going to have all these pointers. It's just like the MP3 pointer funness that you had. You've got to manage a lot of pointers to do this. But it's nothing more than a linked list. So we've got this under control. So I'll say this is, we won't go as far as easy, but I'll say it's somewhat easy. So somewhat easy, somewhat easy, somewhat easy. Okay, what nodes are remaining? The root node's remaining. Are there other nodes remaining? Children of the root. What do all these, and even from the children of the root, there's even more nodes remaining. What's similar about all of these nodes? They all have 2 children. So how would we go about removing the node 33? So 13. So let's find the node 13. Okay, we want to remove 13. Any thoughts? What's sort of a natural intuition? Thought?
The left child and kind of replace.
Okay, so there's one idea that we sort of, I'll sort of do the naive version of your idea, which is that he said we can just take the left child and stick it up here and otherwise maintain the same list. So it'd be nice if we could just take a child and sort of move it up. And is this still a binary search tree? No. And sure, we could recursively do this all the way down, but that sounds like a whole lot of work. So to help us out, we're going to define a couple terms. So we're going to first define a term called the in-order predecessor. Which we'll refer to as the IOP. So the in-order predecessor is, if you think of this list in an in-order traversal, then we want the one that immediately precedes our current node. So the IOP is defined as the max element in the left subtree. And we also can define the other term that's very synonymous, that's sometimes used in binary trees, which is the in-order successor. Which is the IOS, and that's the max element in the right subtree. Or sorry, not max. Minimum element in the right subtree. So the in-order predecessor is the node that comes right before our current node, which is the largest element in the left subtree. The in-order successor is the element that comes right after the current node in an in-order traversal, which is the minimum element in the right subtree. So with this term, we're going to be able to define an algorithm that's extremely simple. And we're going to run it a few times to make sure it works before we go about coding it. So our algorithm is first find the IOP. So looking at our original binary tree, what is the IOP of 13? It's the largest element in the left subtree, so that's 12. So our IOP is 12. Second step, swap the node with its IOP. Swap the element. So we do a swap, and then what's always the last thing we do when we're moving data? Delete it. And I'm going to actually say remove the element. And remove is a keyword here. So we're not going to quite delete it yet, because we'll find that there may be a time where delete's not entirely appropriate, but we need to remove it for sure. So let's see how this works. So we said for 13, the IOP is 12. If we swap 13 and 12, we now have 12 here and 13 down here. and then we remove 13. So is this a binary search tree? Yeah, this looks good. Okay, let's go a little crazier. I want to remove the root. Like that should be a lot harder. Okay, so I'm feeling like it's harder, so I should get red ink out. Okay, it's got to be a hard problem. Okay, we're going to remove 38. What's the IOP of 38? 37. Okay, I'm going to swap 37 now goes here, 38 goes here, remove 38. Is this a binary search tree? Oh, that was too easy. Did we just find a 3-step algorithm that worked? Maybe. Okay, let's edit this tree just slightly. I'm going to start back at the original tree one last time. And let's say there's actually a node 30 down here. So first, before I do anything, did I insert 30 at the right spot? Yeah, I'd go left, then right, then left. Okay, 30's at the right spot. Okay, what's the IOP? Now I want to remove 38 again. What's the IOP of 38? 37. Okay, so 38, we swap this. This is now 37 up here. This is now 38. Oh, can we just wipe this out? No. Okay. We got to now remove this node. So how many children does this node have? 1. So now this is just like updating a linked list. So now we simply removing this node just means and this does look a little, sorry, just because I want to make sure that this arrow looked like it was coming out of the wrong side. So we'll make it go all the way around so it's clear it's coming out of the right side. And then this node gets deleted. Okay. So I have one question for you guys. So we've defined this idea of the IOP as the maximal element in the left subtree. What happens if the element we're deleting doesn't have a left subtree? What's the IOP? Oh, awesome. So what he just said was this great intuition that whenever we're in this case where we have whenever in this case where we're finding the IOP, we're always in the case where we have 2 children. So we never have to worry about the fact that there won't be a left subtree because we already, by the design of this problem, know that we're guaranteed to have a left subtree. The nice thing is we don't have to worry about these special cases. There's always going to be a left subtree, so there's always going to be a max element in the left subtree. Any questions so far? Probably at least one. Is everyone good with this? Question? No. Okay. All right. Yeah. Why can't we move 51 up in place of 37? So, in place of 38 in this case, right? So the original, why can't we move 51, just kind of nuke this subtree and say, oh, okay, I'll just delete it and I'll have 51 point to here. So what do I do with, so now I've sort of got a tertiary tree. So I've got to make a decision on what to do with 40, right? But should 40 always point to 13? So there are ways you could probably recursively do the same thing again and again and again, but then you're looking at a much larger running time. Question? Okay.
Can I say, like, if I remove, I go through the right subtree, then I find the empty left pointer and dump the left subtree to the left one?
So so the question was, can I do a removal in a slightly different way where I find the in-order successor and do the swap with the in-order successor? And the answer was yes, you could do with this IOS as well. In this class, we're always going to use the IOP. We're always going to look through the left subtree. You can look through the right subtree. Totally okay. Yeah? So in this particular case, so the argument is we can then just simply have 40 point to 13 and 51 be the new root. What if 40 had an element 41 over here? Okay. What if it has two children? Yeah, so the reason that 40 looked like it worked was because it was the in-order successor of that tree. So you actually sort of re-implemented this algorithm through one case, and hopefully that intuition helps you understand why this algorithm works. Yeah? So I would say definitely try out your algorithm. You could write a little program to try this algorithm and also see how many operations it takes to do it. So right now, at this point, what is the running time of our remove operation? Not O of 1. I'm going to argue that it's probably not O of n either. Because the first stage, yeah. So the first stage is, what are we doing in the beginning of the algorithm? We're finding the node we want to delete. So we're doing a find operation. So we're finding the node we want to delete. Eventually, we find that node. What do we do once we find that node? We don't swap yet, because right now we just found the element we want to delete. So now we're in our delete step. So we find the IOP, right? So the IOP says, look at my left subtree and go down my left subtree until I find the IOP, right? So I'm going to visit some nodes in this tree, and every step I'm going to go down further. So I'm going to visit one node every level to delete. What do we say that running time is? Yeah, H. We visit one node on every height. So the running time of remove is also O of H. All right, so let's look at the coding of this. So there's a few blanks here. So based on our discussion already, the blanks can either be filled in with no, 1, or 2. So I want you to take a minute and fill in the blanks. Each blank should have the value either no child remove, 1 child remove, or 2 child remove. So fill in those blanks on your worksheet. And what we're looking at here is the do remove function. So this is the function that we're calling once we found the key, once we found the element in our tree that we want to remove. We're now here in this do remove function. All right, so it looks like most of you guys are done writing. So what goes in the first blank? What is it that goes in the first blank? This is the no child remove. What goes in the second blank? 2 child. And the last one? 1 child remove. So there's some elegance about this. So when I went about writing this code, I was like, what's the simplest case? Well, the simplest case is that they're both equal to null. Okay, I'll write that expression first. What's the next simplest case? Well, the next simplest case is they're both not equal to null. And then since we're just handling every case, I left an if statement that's really complicated to write, where you have to say if one is null and the other's not, and if the other's null and not the other's null, or some crazy conditional that might include 4 or 5 different variables. I thought that would be the else statement. So that one might have been hardest to write. So because we're covering the whole state space, we can leave our most complicated Boolean expression as our else condition. So let's just continue diving in. Let's go a little deeper. Let's look at the one that we said the no child remove was easy, and 1 child remove was somewhat easy. So let's look at those. So jumping in further, here's the no child remove function, and here's the 1 child remove function. So the no child remove function says tree node. So let's say I'm removing 37 again. If I'm removing 37, remove 37. Okay, I'm going to store a temp pointer to it. I'm then going to go ahead and set C root to null. So this pointer gets set to null. And then I'm going to go ahead and delete temp. Okay, this seems to implement exactly the algorithm I described. Have a temp pointer hold on to my node, set the tree structure equal to null, and then delete that temporary variable. So why does this modify the contents of the tree directly? What about this allows me to do this? Just like insert, how is tree node passed? Yeah, tree node is passed by reference. So a tree node pointer passed by reference. So whenever we modify the value of that pointer, we're modifying the value in the tree itself. And I actually, when I saw this code, I didn't really love it. Is there a more elegant way to write these 3 lines of code? Can we hack this a little better? Or do we really like these 3 lines of code? What do we think? Anyone? So do we need a temp pointer? I'm going to argue since C node always points to the same value as the same pointer as, so our C node is always the same as temp. Since C node and temp are always the same pointers, a maybe more elegant way of writing the same code is we can simply say delete C node equal null. Right? Oh, sorry. Good call. I mostly work with graphs, so you'll see the node terminology will pop up in a couple of weeks. Yeah, our C root, we can delete C root, and then set C root equal to null. So equivalent code, they're exactly identical. Neither one is more right than the other. So you can write either code, and it'll work the same way. If the left code makes more sense to you, use the left code. If the right code makes more sense to you, use the right code. Whatever kind of intuition you have about kind of how pointers are being passed around and sort of where the pointers are. I find that creating this extra temporary pointer when it's not needed adds to my confusion. But it may add clarity to you. So different people approach it different ways, and both ways are correct. And let's look at the somewhat easy solution, which is sort of just the linked list solution. So I'm going to now try and delete the node 10, which has one child. So I say temp is equal to the current root. Then I say if current root left is equal to null, so current root left is equal to null, then I'm going to say the C root is equal to, so this pointer that got me here is now equal to the right child. And then I can delete temp. So I now am changing C root. So C root's taking on a value here. So I can't just I have to have a temporary variable to keep track of my node. Yeah. Correct. If it was passed by pointer, we wouldn't be able to do this at all. The reason is if we pass this by pointer, then we were modifying we're not modifying the tree itself. So so it's a great question. If either of these are passed by pointer, what's actually happening? So if node child remove was passed by pointer instead of being passed by reference, then what happens is we have a new stack variable that's called C root that points to here, the node we're going to remove. When we set C root to null, I mean, we could even set temp equal to this, like either the 3-line solution or the 2-line solution. We then say C root is equal to null. Okay, awesome. And we're done. And we'll delete the contents of this node. So I've now not deleted the pointer to this node, right? I didn't set that equal to null. I set this pointer on the stack variable equal to null. So because I set the pointer on the stack variable equal to null, instead of the pointer in the tree equal to null, when I then transverse this tree again, I'm going to choop, choop, choop. Oh, I'm accessing memory I freed. What happens? Seg fault. Sadness. So in all of these cases, it's a necessity to pass by reference. So you'll notice that in insert, we pass by reference. Here, we're passing by reference. All right, so let's look at the most complicated of the cases. So binary search tree remove. So the remove case, we said it's a 3-step process. The first step is we need to find the IOP. So if we're moving 38, we're going to get a pointer to the in-order predecessor. So the IOP is here at 37. So the IOP is always going to be the rightmost child of the left subtree. So we said the IOP is going to be the largest value in the left subtree. So the largest value in any subtree will always be the rightmost value. So you can pick any subtree, and the IOP will always be the rightmost value in that particular subtree. So the IOP, so to get the rightmost child, we say if the C root's null, if the right child that's coming up is null, we can just return the current node we're at. Otherwise, we'll recursively find the IOP. So when I saw this code for the first time, I actually thought that I would write it differently. How is the other way you could write rightmost child, find rightmost child? You can write it recursively like this, or write it with a while loop. Yeah. So because when we're finding the rightmost child, what data structure is this? Basically just a linked list, right? We're just finding the rightmost child of a linked list. So the while loop is actually a lot more code. This is a more elegant, more compact solution. But they're both totally the right will get you the right answer. Again, depends on whatever you're most comfortable with. Yeah. Which one's better running time? I'm going to argue that it's going to be pretty negligible, and it's going to depend a lot on system specifics. So you may have to create a whole bunch of stack frames if you make the recursive call, which may slow it down slightly. But there's tons of stack frame optimizations nowadays. So at this level, I wouldn't worry about running time. OK, so we found the rightmost child. And then we're going to assume that we're going to swap the elements. So just for this purpose, where we have really simple things, we can just swap the keys. That maintains the tree structure. This may need to swap data to, or move node if we've got lots of data. So this is our swap operation. We'll assume the swap operation works, and we'll remove the IOP. I'm going to argue in the last minute that this code is broken. It doesn't work. Why doesn't it work? It's for the same reason we've gone over something 3 times so far this lecture. The IOP is, where is the variable IOP stored? On the stack. So we've now copied this value of IOP onto the stack. So when we do removal of IOP and call back to this function, all the guarantees we made about how this is going to update the tree structure is now broken. We argued many times today why everything has to be passed by reference. So we can't have any stack variables containing pointers to our trees. So how do I fix this? That's a great kind of like, every time I've seen this, I just add in ampersand. So there's actually a new thing that you've never seen before, and we can have what are called reference variables, just like we have pass by reference parameters and return by reference. If we say tree node star ampersand IOP, we now have a reference tree node pointer that now takes on the memory address of the return value as opposed to creating a new stack variable. So now, by adding the ampersand, we've created ourselves a reference variable which now doesn't create stack memory and allows all of our guarantees that we've made up to this point to work. Last question, what was the running time of remove? O of H. So this continually works, and we've got a running time of OH. And on Monday, Cinda will be back, and she will talk about how do we control the H in terms of N. See you guys on Monday.